T-minus 10, 9, 8,
The clock is
7.
operating. We're underway.
Tranquility Base here. Endeavor, go at throttle up.
Welcome. I am monitored to respond to the name Robbie. I was created by Dr. Morbius on the main sequence star Altair, as documented in the classic science fiction movie Forbidden Planet. On Earth, I've been starring in movies and television for nearly 50 years, and I am the most famous robot of all time. Modest, too. Well, enough about me. When I heard that NASA was in need of a robot helper for the astronauts, I volunteered for the job. But wouldn't you know, NASA is already creating their own robot designed to meet their special needs and spaceflight requirements. I guess NASA is not ready for a famous robotic actor like me to work on the space station. On this episode of NASA Connect, you'll be introduced to the systems on this robot and the math, science, and technology that go into designing a robot for astronauts in a spacecraft. In your classroom, you'll do a cool hands-on activity to solve a problem the engineers are facing. How to reduce the size of the robot. And using the online activity, you'll learn about the forces that affect how the robot moves in space. Stay tuned as host Jennifer Pulley takes you on another exciting episode of NASA Connect. PSA, the astronaut's helper.
I'm Jennifer Pulley, and welcome to NASA Connect, the show that connects you to math, science, technology, and NASA. We're here at the Tech Museum of Innovation in San Jose, California. Now, you know, this episode of NASA Connect is all about robots in NASA's space program. Now, you may think of a robot as a mechanical creature that walks around. But did you know that the first person to use the word robot wasn't a scientist at all? In fact, he was a Czechoslovakian writer named Karel Čapek. In Czech, the word robota means forced labor. Now, in his play, Rossum's Universal Robots, Čapek used the word to describe electronic servants who turn on their masters when given emotions. In 1941, science fiction writer Isaac Asimov first used the word robotics to describe the technology of robots and predicted the rise of a powerful robot industry. In the 1950s, it seemed like robots were featured in nearly every science fiction movie and TV show.
Like me!
But since then, robots have moved from science fiction to science. Unimate was the first industrial robot used in a General Motors automobile factory in 1961. Since then, the field of robotics has advanced as computers have become more powerful and compact. With powerful computers, scientists can program robots with artificial intelligence so that they can make decisions.
When I let go, it will straight away start again into the right slinky action.
During the course of this program, you will be asked several inquiry-based questions. After the questions appear on the screen, your teacher will pause the program to allow you time to answer and discuss the questions. This is your time to explore and become critical thinkers. But before we take a look at all the different types of robots, here are some questions for you to think about and discuss. If you could have your own personal robot, what would you like your robot to do? How intelligent would your robot have to be? How would you communicate with your robot? Teachers, pause the program, and students, write down what you think. Okay guys, now let's meet a robotics engineer and learn about some of the different types of robots being built at NASA.
Thanks, Jen. My name is Dr. Ayanna Howard here at JPL, NASA's Jet Propulsion Laboratory in California. This is the Mars Yard, but we actually test the rovers before sending them to Mars. NASA uses robots to do things that are too dangerous for humans. Robots are used to explore planets and even maintain and repair the outside of vehicles, such as the International Space Station.
Hey guys, did you design your robot to do things that are too dangerous for you to do, or too tedious?
Robots are the tools that allow scientists to reach beyond the Earth to other planets. In the 1970s, NASA sent a spacecraft to explore the planet Mercury. It was called the Mariner 10 probe. It flew past the planet 3 times and took thousands of photos. For the first time, scientists could actually see what the surface of the planet looks like. Rovers are actually robots that can land on other planets and move around. Sojourner was the first of the rovers to land on the planet Mars. Its mission was to test the rocks in the air. It takes several minutes for a command signal to reach a robot in space. Sometimes a robot can't wait for mission control. It has to make decisions on its own. This ability is called autonomy. Sojourner was semi-autonomous, which means it can make some decisions on its own. I work on autonomy for Mars exploration. We want to land precisely where there are good samples to study. We want to be careful so we don't hit any cliffs or boulders on the surface of Mars. We can use airbag, but we can't land precisely. That's why we use artificial intelligence. Not only can we use artificial intelligence to land the spacecraft safely on Mars, but we can use the same intelligence to give the rovers a little bit more smarts when they actually get to the surface. The future of space exploration depends on building these smart robots.
Thank you, Dr. Howard. Okay guys, let's head over to the NASA Ames Research Center here in California to learn more about robots from researcher Maria Bullitt. What a cool robot! Tell me about K9.
K9 is a prototype of a Mars exploration rover with stereo cameras, so it can take 3D pictures, and it's got an arm that lets us practice putting science instruments on rocks and on soil.
Okay, Maria, so how will K9 know what to do on Mars?
It will receive instructions from Earth on what experiments to conduct. A robot's shape, capabilities, and method of locomotion depend on what you want it to do.
Well, besides K9, what other robots does NASA have?
We're testing planetary robots in the Rio Tinto, or Red River region of Spain, where the terrain looks a lot like the surface of Mars. That robot is built to burrow into the ground and look for signs of life. Robots are also being built to maintain and repair the outside of a space vehicle. Robonaut is a humanoid robot that performs tasks that other robots can't.
Well done.
From the safety of the space station, an astronaut controls the movement of Robonaut's hands with a control system known as telepresence. AirCam is another experimental robot that's being designed to fly outside the space station and lets astronauts inside see what's going on outside. Scientists are also designing robots to help us out here on Earth. Kismet, the sociable robot.
Oh, did he say he loves me? I love you too.
Scientists at MIT are working on building a robot that can interact with people.
So there are many different kinds of robots that are designed to work in many different environments.
That's right. Robots may need parts that can see, parts that enable them to move around, and parts that make decisions. All these parts must work together for the robot to function. They make up a mechanical system.
Thanks, Maria. So, can you think of a mechanical system? Remember, a mechanical system is something that's made up of many different parts, and those parts work together so the system will function. Now it's time for your teacher to pause the program and for you to answer the following questions. What is a mechanical system? And what are some examples of mechanical systems? You know, we use the word system to describe something that is made up of different parts that must work together in order for the system to function. A car, it's a mechanical system, and it's made up of different parts, like an engine, the body, the doors, and the wheels. Each part can't get you where you want to go, but when the parts work together as a mechanical system, you can go places with it. The International Space Station is also a mechanical system, with parts in it that work together as a whole. Say, do you know how busy the astronauts are on board the International Space Station? Well, let me tell you, each astronaut conducts hundreds of experiments for scientists in the United States and in many other countries, so they could use a little help. Now, let's go to NASA Ames Research Center and meet engineer Yuri Gaudiak, who thought of a way to help the astronauts. Yuri, tell us about how you're going to help the astronauts on station.
Well, in addition to doing experiments, the astronauts have to do a lot of logistics, inventory tracking, air samples, and water samples. So as a research team, we wanted to help offload those activities. So we developed a robot that we were inspired by Star Trek with the tricorder and by Star Wars with a floating orb. And what we added to that was the ability to do scheduling, procedures, training, and then also environmental sensing. And we wanted it to be mobile so it could go follow the crew or go off on its own and actually monitor by itself. So what we developed is the personal satellite assistant.
Yuri, that is so cool. You know, let's find out more about this robot that NASA is building to help the astronauts. As you watch the program, think about your robot as a system and the parts it will need in order to perform the tasks you assign to it. Now guys, this is the PSA, or Personal Satellite Assistant Laboratory here at the NASA Ames Research Center. And this is Dr. Keith Nicewarner.
Hi.
How are you, Keith?
Good.
Tell us, what will the PSA be able to do?
Well, the PSA will be able to check the inventory, the temperature, the air pressure, and air composition on the space station. It needs to move around by itself in microgravity, avoid things that get in its way, and communicate with computers and people like mission control and astronauts. It must also understand the astronauts' commands and let the astronauts know when something needs to be addressed.
So Keith, it sounds like the PSA is a system that's made up of many other systems that all must work together.
That's right. A lot of this work has never been done before. We've never had a robot that flies around by itself in microgravity with humans for long periods of time and knows what to do and understands what you say. What is microgravity? Microgravity means that you feel very little of the force of gravity because the ISS and everything in it is in free fall as the ISS revolves around the Earth.
Want to learn more about microgravity? Well, then check out the NASA Connect program, Who Added the Micro to Gravity? Now back to the PSA.
PSA has a propulsion system, a sensor system for measuring things like temperature and pressure and detecting obstacles. There's also a navigation system for knowing where it is in the station and knowing how to get from place to place. It also has an artificial intelligence system so it can make decisions, and a communication system so it can communicate with astronauts and ground control.
How will the PSA see where it's going so it can avoid obstacles that may get in its way?
The PSA will use proximity sensors to tell if something is nearby. All these little holes are sensors. We're using sonar or sound waves.
Sonar. Isn't that what bats use to navigate and what whales and dolphins use to locate schools of fish?
Yeah, it's the same idea. PSA also has 4 pairs of cameras for stereo vision.
What is stereo vision?
Well, 2 eyes enable depth perception. With only 1 eye, it's difficult to tell how far away something is. Most animals have 2 eyes. The PSA has 8 cameras, which serve as eyes to perceive depth all around it. The cameras will also be used to show mission control what's happening on the space station and allow video conferencing with the astronauts. The PSA also has a thermal imager that looks for hot spots. This is very important for doing things like looking for an overheating rack. The PSA will also have a laser pointer on it that can be controlled from the ground. Engineers on the ground will be able to point to things on the space station and the astronauts will know what they're referring to.
Wow, the PSA is going to be busy. What other responsibilities will it have?
Well, they can keep track of the astronauts' schedule, alert them when something needs to be done, and give them instructions when they need to repair something.
So the astronauts wouldn't have to use their manuals anymore. The PSA would tell them what to do.
That's right. The manuals are all in electronic form, either in the computers on the ISS or the computers at Mission Control. So the PSA can access the information from the computers and read it to the astronauts or show it to them on the PSA's monitor.
So the PSA is a system that contains other systems so that it can work.
That's right. The PSA has sensor, navigation, propulsion, communication, and artificial intelligence systems.
Thanks, Keith. So guys, what mechanical system did you choose? Now is the time for your teacher to pause the tape so you can discuss your mechanical systems. Here are some examples of mechanical systems you probably come in contact with every day. Dr. Nicewarner mentioned several PSA systems. Now it's time to look in detail at one of those systems. Hi, I'm here with Dan Andrews, and he's a research engineer on the PSA team. Hey, Dan.
Hey, Jennifer.
Tell me a little bit about what you do here.
I'm a controls and automation engineer at the NASA Ames Research Center. My team is working on evolving the PSA robot vehicle. In designing the propulsion system for the PSA, we had to keep in mind that things move differently on the International Space Station than they do here on Earth. Jen, this would be a good time to see if students can describe two ways in which motion of something in the space station is different than the way things move on Earth.
Dan, I think that's a great idea. Teachers, now is the time to pause the program, and students, write down two ways that you think items move differently in space than they do here on Earth. If you mention something about microgravity, well, you're on the right track. You may have seen microgravity on the International Space Station. It appears that items are floating on the International Space Station, but in fact, everything is moving or falling at the same rate. To learn more about microgravity, check out the NASA Connect program, Who Added the Micro to Gravity. So did you mention something about friction or lack of friction? Well, you're also on the right track.
The motion of an object on the space station is like moving on ice, or throwing a ball versus rolling it on the ground. This is a functional prototype of the PSA, which means it's a working model. We have also tested the prototype on a granite table, which has very little friction, like an air hockey table. So it's a simulation of what motion is like on the ISS.
So Dan, how does the PSA move?
In this functional prototype of the PSA, we're using fans. We have 6 sets of fans located around the robot. Air is drawn in from one side of the fans and expelled out the other side. That creates a force on the robot and enables the PSA robot to move. It's important that we use a quiet propulsion system because it's relatively noisy on the space station and we don't want to aggravate the problem. We also need to test the PSA in 3 dimensions. We need to allow it to move up and down, left and right, forward and backward. Within this facility, we've created a smart crane, which lets the PSA move as if it's in space. We use this crane to test how the PSA can do obstacle avoidance and just generally get around.
Dan, aren't there some laws or rules of motion that affect the way things move?
That's right. There are laws of motion that apply whether you're here on Earth or on the ISS. Sir Isaac Newton figured out the laws of motion way back in the 1600s. He said that an object at rest will remain at rest.
Sure, Dan, that makes sense. If something is sitting on a table, for instance, it will stay there until someone moves it or some force moves it away.
Newton also said that once an object is in motion, it will keep moving unless you apply a force to it, like giving it a push or a pull.
Now, wait a minute, that doesn't make sense to me. Doesn't everything just stop moving eventually?
Things stop moving because of gravity and friction. In microgravity, you can really see Newton's laws at work.
Let me see if I have this straight. If something is moving, it may or may not have a force acting on it. And to stop it, you have to apply a force?
That's right. On the ISS, the PSA will float because of microgravity, and it will keep moving once you push it.
So Newton was a pretty smart guy. I mean, he thought of this 300 years before NASA sent astronauts into space.
Once you apply a force, like pushing the PSA, it will move and keep moving. In fact, the PSA will keep moving even if you turn the fans off and apply no force at all.
Okay, so how do you stop the PSA?
You have to turn the fans on again and apply a force in the opposite direction.
Now you can check out the way the PSA will move on the ISS. Here's what Newton said. An object at rest will remain at rest. An object in motion will remain in motion unless a force acts on it. Now it's your turn to try the online activity found at the NASA Connect website. Your challenge is to get the PSA to the overheated racks before the time runs out. Each click gives the PSA 1 unit of force in the direction of the arrows. Remember Newton's law. The PSA will keep moving unless you apply another force to it in the opposite direction. Your teacher will now pause the program so that you can go to your computers and check out the activity.
I gave the PSA too much force. It hit the side of the ISS.
The PSA keeps moving after you have applied a force to it.
You have to apply a force in the opposite direction to stop the PSA.
Newton also had something to say about motion and the mass of objects. The more massive an object is, the more force is required to accelerate it or to stop it.
So if the PSA is very massive, for instance, it's going to take a lot of force to get it moving and a lot of force to stop it.
You're right. The greater the mass of the PSA, the more force it takes to slow it down. The fans have to work harder. If we make the PSA lighter, it requires less force to slow it down than to stop it. If the PSA was going to go too fast, it might bump into the side of the ISS. So we need to make the PSA as light as possible. The current model that you see here is the 12-inch working prototype. Our goal is to reduce the PSA size down to this 8-inch diameter model. With the invention of the transistor, computers and other electronic gadgets became smaller and smaller.
Oh, that's right. You know, when our grandparents were kids, they listened to radios that were like large pieces of furniture. Today, radios and digital players are really tiny.
That's right. A computer with the same power as this PDA filled this huge room. The PSA has a computer inside it, and in addition, the PSA can connect to computers on the space station or on Earth with a wireless connection and use the computing power of those computers.
So the PSA can be small because it doesn't need a big computer inside of it. But why is it round? And how do you make the shell round?
Round shapes don't have any sharp corners, so the PSA won't accidentally damage the ISS. We designed the round shell with a computer program for solid modeling. Once the design is complete, we send an electronic file to the manufacturer to create a shell. The process is called stereolithography, or SLA. To make the PSA smaller, we need to redesign and shrink the parts in the PSA so that they fit into a smaller sphere.
Oh, wait a minute. I don't know if that's the best way to do it.
When we make things smaller, though, we have to keep some things in mind. For example, the computer that's in the PSA needs to have space around it so that it can stay cool. The computer gives off its heat from the surface area of the board, which means we need to provide space for cooling. Additionally, when we consider shrinking the fans to fit in a smaller PSA, we discovered they became very inefficient, forcing us to move to a blower design. It's similar to how a leaf blower works.
Okay guys, let's review some math concepts so you can figure out how to fit your parts into the PSA. This is a rectangular prism. Now each one of its 6 sides is a rectangle. The surface area of the rectangular prism is the sum of the areas of the 6 sides. The volume of a rectangular prism is the area of the base times the height of the prism. Let's take a look at cylinders. The base of a cylinder is a circle. Let's take a look at the parts of a circle. The circumference is the distance around a circle. The radius is the distance from the center of a circle to any point on the circle. The diameter of a circle is twice the radius. Thousands of years ago, mathematicians measured the circumference of circles and divided the circumference by the diameter. They always came up with the same number, around 3.14. This number is called pi. Now, watch this and see how we can find the area of a circle. We cut up the circle and move the pieces around. Now, the area is the width times the height. The width is pi times the radius, and the height is the radius. The surface area of a cylinder is the sum of the areas of the 2 circles and the area of the side, which is really a rectangle. The volume of a cylinder is the area of the circle times the height of the cylinder. Now, here's the challenge. Find the length, height, and width of a rectangular prism that has a volume of 24 cubic inches, fits into an 8-inch PSA, and has as much surface area as possible. Find out whether a tall cylinder or a wide cylinder has more surface area when the volume stays the same. You can download the files for this activity from the NASA Connect website. It's now time for your teacher to pause the program so you can take the challenge. Use your imagination, draw figures, take measurements, and do calculations.
We're Miss Dance's 7th grade math class.
The students at Graham Middle School in Mountain View, California took the challenge. Let's see some of their results. Recall the 2 questions in this activity. 1, what are the dimensions of a rectangular prism that has a volume of 24 cubic inches, fits into an 8-inch PSA, and has the maximum surface area? And 2, if the volume stays the same, does a tall cylinder or a wide cylinder have more surface area?
We're going to get the biggest surface area by using points. 2 inches. What do you guys think? Is that going to fit? Remember, our goal is thinking about how to maximize surface area.
The surface area was 77.6.
What are we going to say? What dimensions are we going to recommend?
6 by 5 by 0.8.
So guys, what did you find?
When you flatten a rectangular prism, the surface area increases.
You can get different answers depending on how high you make the rectangular prism.
When the radius increases, the surface area of the cylinder increases.
Okay, let's summarize. The surface area of a rectangular prism is the sum of the surface area of its 6 sides. The volume of a rectangular prism is the length times the width times the height. A rectangular prism has the minimum surface area when it's a cube, and the surface area increases as you flatten it. The surface area of a cylinder is the sum of the areas of the circles at the top and bottom, and the area of the side. The volume of a cylinder is the area of the circle at the bottom times the height of the cylinder. When the volume is the same, a tall cylinder has less surface area than a wide cylinder.
We have to do calculations like this when we lay out the design of all the components of the PSA.
Okay, so Dan, what is the future of the PSA?
Well, once we're able to make the PSA smaller, we'd like to consider a PSA which could further interact with the spacecraft. Imagine a PSA with arms that could actually push buttons, retrieve tools, and better interact with the ISS.
Well, developing effective artificial intelligence is a big challenge, and being able to understand what the astronauts say is especially difficult because our brains understand things in context or the situation we're in.
Well, a critical part of the future of the PSA is the vision system. We need vision for everything from navigation and control to identifying hazards to doing inventory tracking, and also to recognize the crew, because we need to customize schedules and training procedures to go with a particular crew member. And we also use it as sort of remote eyes for the ground folks that are running the operation, so they can inspect the station through the eyes of the PSA. And being able to interpret what you can see will save us a great deal of time.
My thanks to Yuri, Keith, and Dan for all their information on the PSA. And don't forget, keep checking the PSA website for the latest developments on this personal satellite assistant. Well, guys, that wraps up another episode of NASA Connect. NASA Connect would like to thank everyone who helped make this program possible. Say, got a comment, a question, or a suggestion? Well, then email them to connect@lark.nasa.gov. Or pick up a pen and mail them to NASA Connect, NASA Langley Center for Distance Learning, NASA Langley Research Center, Mail Stop 400, Hampton, Virginia 23681. So, until next time, stay connected to math, science, technology, and NASA. And maybe one day, you'll have your own personal assistant. See ya! So, Maria, besides K9, what other robots is NASA testing? NASA. Well, here I am. Let's see. What do you think? So the PSA is a system that has other systems working within it to make it work. Go ahead and get brain freeze. Okay, sorry. I'm thinking of like burgers and things. Turn the wrong way.
Captioning funded by the NAC Foundation of America.